Welcome to video number 11. We're back to a prime number, which is always good news. This video, although it's to help everyone with their maths and inspire them to be better mathematicians hopefully, is a particular response to a student request from one of my earlier videos. So about a week ago I put up a video which had an integration question on to do with cyclic functions. The integration was e to the x times sine x integrated with respect to x, and I said, oh, what a great example for you to try at home. And then the student came to me and said, but how do we do it? Actually it's a lovely question. It's something you do normally as part of lessons, and it's great to go through and get practice of. Obviously this student, I won't embarrass him by mentioning his name, but I was reminded as I just came back from Sainsburys and he was working on the till next to where I paid for my things, so that will narrow it down. This was the question, and to integrate it we use integration by parts, kind of part of C4, and it turns out particularly nice because of how it repeats. Now when you're doing integration by parts, obviously there's real importance about which you pick for u and v. So the formula that you get in the formula books at the top here, and if you pick the right thing you can make your question a lot easier. Pick the wrong thing and you might not get the result. In some cases it doesn't matter. In this case it doesn't matter. The magic here isn't picking the right expression for u and v. It's how you deal with the recurring nature. So I'm just going to go through this example and show you how to terminate a cyclic pattern in this way. You may at this point notice a couple of things. If you're not familiar with integration by parts, you'll notice there's a whole load of constants missing, and we don't need to necessarily worry about these when integrating by parts, as long as we either remember that they're there and at the end add one on in an appropriate place, or we're evaluating the integral between 2 points. So I don't need to worry. The second thing you might notice is my pen is also running out, so hopefully it will make it through. If not, there might be some fancy video editing going on. Here's quite important. At this point, you can probably see we're going to have to do integration by parts again. Some people at this point start then to worry because they can't see how it's ending, and that's okay. But it is really important that if you've picked the exponential term for your u, which I did here, that I then continue to pick the exponential term when integrating the second half of this expression, also as my u. Okay, and this is the final step before I do something that's clever that was puzzling the student that has no name. What I've got here is an expression that looks very familiar. It hopefully would be familiar because this is exactly the same as what we had at the start. And if we can engineer this by pulling out constants or other processes, then what we can do is label our initial question. And because I've kept working on the whole equation throughout, value on my right hand side of the equation is still equal to the value at the start. So I've still got I, in this case, equals this, but now I've got exactly the same here, so I can substitute I in for that. Neat little trick, and the following step now seems quite trivial. And I know my students would never let me forget it if I didn't remember my constant of integration at the end there for my final answer. Okay, so that's the solution. And I know a lot of you that watch these videos would not have done integration by parts yet, and although I'm sure a lot of you would have been interested to see how that works, if I set a puzzle on it, that wouldn't really be fair now, would it? So the puzzle I've set you today is still about cyclic patterns, but this one I found was very different. Here's a number. You don't need to know integration by parts to be able to understand what that number is. 142,857. There's some nice properties of this number. You'll notice there's certain digits missing out of all the digits I could have. There's no 0, 3, 6 or 9. Yeah, maybe there's a pattern there as to why I picked these. The thing I want to talk about though is if you times this number by 2 and then write down your answer, then times it again by 3, write down your answer, then by 4, write down your answer, then by 5, in fact also by 6, you should see a pattern. I knew this pattern, I didn't find this by accident, I knew this would happen because of how I generated this number. So I'm wondering if you can work out why that's important, and why it does that, and where this feature comes from, and actually some of you might recognise those numbers and seen them in that particular order before. The order is specific, I can't just jumble them up and have the same thing happen again. So have a think about that one, see what the results are, see if you can work out what's going on, and if you have any reasons about to justify the pattern that you get, that'd be great to hear what those are. So if you can scribble them in the comments, I'll look forward to reading them.